Welcome to this video. In our video titled, Model of Mechanical Translational System, we learn to quantify the opposing forces acting on the mechanical translational system for the given input. With these values of opposing forces, we can determine the transfer function. This video will explain how to quantify the opposing forces acting on the mechanical translational system. Write the differential equation for the given mechanical translational system. Determine the transfer function of the mechanical translational system. Here is the model of a mechanical translational system. We are going to determine the transfer function of this system. To calculate the same, first, you need to draw the free body diagram of each mass in the model of the system. Here, the system has two mass bodies, M1 and M2. Let us now consider mass M1. F of t is the input force acting on mass M1. Force due to mass M1, dash pot B, and springs K1 and K2 are the opposing forces. F M1 is the force due to mass M1. Fb is the force due to dash pot B. F K1 is the force due to spring K1. And F K2 is the force due to spring K2. Y1 is the displacement of the mass M1. The diagram that represents all the forces acting on a body is called the free body diagram. Now, let us quantify the opposing forces acting on mass M1. The opposing force F M1 offered by the mass equals M1 multiplied by acceleration d square y1 divided by dt square. The opposing force Fb offered by the dashpot equals b multiplied by velocity dy1 divided by dt. The opposing force F K1 offered by the spring K1 equals K1 multiplied by displacement y1. The opposing force F K2 offered by the spring K2 equals K2 multiplied by displacement y1 minus y2. Since the spring K2 is subjected to the displacements y1 and y2, we should consider the resultant displacement while calculating the opposing force. Here we are referring to the mass body M1. And the displacement corresponding to M1 is y1. So, we should subtract y2 from y1 to calculate the resultant displacement. The dynamic equation or differential equation of motion for free body diagram M1 is f of t equals fm1 plus fb plus fk1 plus fk2. Substitute the known values of opposing forces in this equation. Let us take Laplace transform for this equation. We know that the Laplace transform of d square y1 divided by dt square is s square into y1 of s. Laplace transform of dy1 divided by dt is s into y1 of s. Laplace transform of y1 is y1 of s and y2 is y2 of s. Laplace transform of f of t is f of s. Now, rearrange this equation to group the terms having y1 of s. Name this equation as 1. Let us now consider mass m2. There is no input force for mass m2. And only the spring K2 is connected to m2. So, the force due to mass m2 and spring K2 are the opposing forces. F m2 is the force due to mass m2. F K2 is the force due to spring K2. Y2 is the displacement of the mass m2. Now, let us quantify the opposing forces acting on mass m2. The opposing force F m2 offered by the mass equals m2 multiplied by acceleration d square y2 divided by dt square. The opposing force F K2 offered by the spring K2 equals K2 multiplied by displacement y2 minus y1. Since the spring K2 is subjected to the displacements y1 and y2, we should consider the resultant displacement while calculating the opposing force. Here we are referring to the mass body m2. and the displacement corresponding to m2 is y2. So, we should subtract y1 from y2 to calculate the resultant displacement. The differential equation for free body diagram m2 is f m2 plus f k2 equals 0. Substitute the known values of opposing forces in this equation. Let us take Laplace transform for this equation. We know that the Laplace transform of d square y2 divided by dt square is s square into y2 of s. Laplace transform of y2 is y2 of s and y1 is y1 of s. Now, rearrange this equation to group the terms having y2 of s. Name this equation as 2. Using these two equations, we can determine the transfer function of the given mechanical translational system. We know that the Laplace transform of output divided by input at zero initial condition is the transfer function. Since the system has two displacements or outputs y1 and y2, we can represent the transfer function in two ways. So, the transfer function of the given system can be represented by y2 of s divided by f of s or y1 of s divided by f of s. Let us now determine the transfer function y2 of s divided by f of s. Equation 1 has the term f of s. To determine the transfer function y2 of s divided by f of s, we need to remove the term y1 of s in equation 1. So, rearrange equation 2 to represent the value of y1 of s. Then, substitute the value of y1 of s in equation 1. Rearrange this equation to group all the terms having y2 of s. Finally, move f of s to the right-hand side of the equation and the terms within the bracket to the left-hand side of the equation. This equation, y2 of s divided by f of s, represents the transfer function of the given system. If you want to calculate the transfer function y1 of s divided by f of s, rearrange equation 2 to represent the value of y2 of s. Then substitute this value in equation 1. This brings us to the end of this video. In this video, we learned to quantify the opposing forces acting on the system, write the differential equations governing the system, calculate the transfer functions of the given mechanical translation system,